effectiveness, or as it is commonly called, LTE. What is it, and what causes it?
Can you tell me what loss of tail rotor effectiveness is?
Loss of tail rotor effectiveness is? Loss of tail rotor effectiveness is sort of a misnomer.
Loss of tail rotor effectiveness is an uncontrollable yaw to the right.
Loss of tail rotor effectiveness is a tendency of the aircraft
It's the loss, or it's the inability of the tail rotor to be effective during all phases of flight.
What if this question had been asked of you? Could you have correctly stated what LTE is and what causes it? LTE is defined by the operator's manual as the occurrence of an uncommanded and rapid right yaw, which does not subside of its own accord and which, if not quickly reacted to, can result in loss of aircraft control. Now that LTE has been defined, it is vitally important for all to learn the causes and the proper corrective actions. The Training and Doctrine Command, TRADOC, and the Army Materiel Command, AMC, Joint Special Study Group investigation of the OH-58 LTE phenomena has identified 3 relative wind regions which adversely affect aircraft controllability. They are weathercocking, vortex ring state, disk vortex. We will look at each region individually. The influence of the weathercocking region will be felt when the relative wind azimuth is 120 degrees through 240 degrees. Besides causing a high pilot workload, tailwinds are a yaw rate accelerator. If the pilot allows the tail of the aircraft to move into this region during a right yaw, the yaw rate can increase very rapidly. When flying in a tailwind condition, the pilot must, by smooth application of pedals, not allow a yaw rate to build. The pilot must remember that a tailwind can rapidly accelerate a pilot-induced right turn. A tail rotor vortex ring will form with a relative wind azimuth of 210 through 330 degrees. To counter the main rotor torque, the tail rotor produces thrust to the right. As a result, the tail rotor wash is to the left. A left crosswind opposes this wash. These wind tunnel segments will show the effects of a left crosswind. The model is positioned in the wind tunnel at the heading for a relative wind azimuth of 270 degrees, and the tail rotor is operating at a constant pedal setting. Smoke is used as an airflow visualization device. This sequence shows the tail rotor operating in the normal working state with a crosswind of approximately 5 to 10 knots. The tail rotor is just entering the area of unsteady airflow. Pilot workload in this area will begin to increase as he attempts to compensate for the aerodynamic oscillations. As the wind velocity is increased, the unsteady airflow also increases. With an approximate wind velocity of 10 to 20 knots, the tail rotor vortex rings become visible. Observe that a ring will form and build in size. As the ring increases in size, its strength will weaken, allowing the left crosswind to blow it away from the tail rotor. This dissipating action is evident by diffusion of smoke. It is the formation and shedding of these vortex rings which cause the tail rotor thrust oscillations to occur. Notice that the rings form and dissipate very rapidly and at random intervals. It is this mechanism that produces the high pilot workload associated with flying in this region. Observe the motion of the tail rotor and vertical fin. The model is rigidly mounted, thus the tail boom is shaking. In an actual aircraft, the pilot would see this as a rapid left and right yaw moment. As the left crosswind velocity increases from approximately 20 to 35 knots, the tail rotor moves into the windmill brake state. Notice that as the wind speed increases, the vortex rings will become less apparent and will eventually disappear altogether. Pilot workload in this area will begin to decrease as the left crosswind velocity increases and the airflow through the tail rotor once again becomes smooth. The pilot's major concern in this area would be the weather vaning capabilities of this crosswind. The wind is strong enough to force the aircraft into a left yaw, which the pilot must correct with right pedal. If the application of right pedal causes the aircraft to yaw right to where the relative wind moves into the weather cocking region, the yaw can rapidly progress into a spin. The final region to look at is disk vortex. This becomes a factor with a relative wind azimuth of 280 through 330 degrees, and when the velocity is between 10 and 30 knots. Vortices are generated as a function of lift. The greater the lift, the stronger the vortex. This segment shows the strength and size of the vortices created by a heavy jet. A rotary wing aircraft also generates vortices, and these vortices move with the relative wind. The size and intensity of the main rotor tip vortices can be seen here as they trail downwind. Notice that the vortices are sharply defined. This wind tunnel sequence shows the top view of the OH-58 main rotor disc vortex. The smoke is placed on the edge of the main rotor disc. Notice again that the edge of the vortex is well defined. The model is now positioned with a relative wind azimuth of 330 degrees. An actual aircraft at this point would have a tendency to yaw left into the relative wind. To maintain a constant heading in this position, a pilot would be applying a slight amount of right pedal pressure. The model is now positioned with a relative wind azimuth of 320 degrees, just 10 degrees difference from the previous position. The diffusion of smoke indicates the tail rotor is now operating within the influence of the main rotor disc vortex. It is at this point that a sudden tail rotor thrust reduction will occur. The thrust reduction occurs because of the airflow changes experienced at the tail rotor as the main rotor vortex moves across the tail rotor disc. The pilot must be prepared to apply additional left pedal to prevent the aircraft from yawing right. This sequence shows a side view of the main rotor disc vortex when viewed from the left. It clearly shows the main rotor vortex as it is blown rearward by the wind. As the model is yawed to the right, notice how the main rotor vortex intersects the tail rotor disc. Again, it is this vortex and its turbulence which causes the sudden decrease in tail rotor thrust. It is important to note that there are two areas of overlap. Control of the right yaw rate is critical when flying in either of these areas. The pilot must be aware that left pedal application is critical to prevent a right yaw from progressing into a spin. Now that you have seen what causes a loss of tail rotor effectiveness, the next obvious question is, what can I, as the pilot, do to avoid an LTE situation? Therein lies a problem. As a scout pilot in the terrain flight mode, you cannot avoid an LTE conducive environment. As you maneuver about the battlefield, you will be subjected to continuously changing wind directions and velocities. So, how can you reduce the likelihood of encountering LTE? There are 5 important points for you to remember to help avoid an LTE situation. The first 4 are specific points that are culminated in the 5th point. They are: 1. Develop a feel for the aircraft and how it will react under varying wind conditions. 2. Develop the ability to read the winds. By observing trees, smoke, grass, and other objects, you can estimate the direction and velocity of the wind. 3. When possible, make left turns. When making a left turn, the pilot will, in effect, be increasing the tail rotor thrust and therefore be more sensitive to the need for left pedal input. 4. Avoid excessive movement of the flight controls. Over-controlling increases the likelihood of getting behind the aircraft. By smoothly coordinating control inputs, the odds of encountering an LTE situation can be reduced. 5. Fly the aircraft. This is really a summation of the above 4 points. Terrain flight is very demanding and requires the pilot to give the flying of the aircraft his full attention. You must be sensitive to what the aircraft is doing. You might be thinking, I always fly the aircraft. What a dumb statement. If this is running through your mind, then let me ask you. As you could see from these scenes, you think you are flying the aircraft, but in reality, are you? In all situations, the pilot's first priority is to fly the aircraft. If you find yourself in an accelerating, uncommanded right yaw, it is critical that you simultaneously apply left pedal and forward cyclic. The use of the collective will be at the pilot's discretion based on altitude. This sounds simple, but remember, this procedure must be done instantly. Other factors which may be present can significantly influence the severity of the onset of LTE. These factors include gross weight, density altitude, low indicated airspeed, power droop. You cannot, as a scout pilot, avoid the environment that could lead to an LTE occurrence, but you can, by understanding what causes it, avoid the situation in most cases. You must, above all, remember to always fly the aircraft. Based on test results from various organizations, the U.S. Army Safety Center feels the main rotor disc vortex effect is the most significant influence in entering LTE. Additionally, this region produces the most rapid and violent onset of LTE. As a result of numerous accounts of LTE, the U.S. Army Aviation Systems Command, AVSCOM, has developed product improvements for the OH-58A and C helicopters. When applied over the next few years, these PIP should significantly reduce the incidence of LTE. In a March 1984 message, the Vice Chief of Staff of the Army directed, in order to prevent loss of tail rotor effectiveness accidents with the OH-58s, which have not had the power droop and improved tail rotor product improvements installed, the following restriction is imposed. OH-58s without the above PIPs will maintain a minimum of 35 knots indicated airspeed in forward flight, regardless of altitude. The exceptions are A, approved OH-58 terrain flight training and operations. B, landing, takeoff, and hover in ground effect. C, maintenance test flights. D, life-threatening situations, actual emergencies. And E, special missions when approved by Aviation Commander 05 or higher on a case-by-case basis.